Welcome to Networks Professionals.
Welcome to the explainer. So if you've ever stared at a router's spec sheet, looking at all those letters like 802.11ac, AX, or B, and wondered what on earth that alphabet soup actually means for your daily connection, well, you are definitely in the right place. Today, we're cutting through the jargon and decoding the IEEE standards to see exactly how the invisible web connecting all of our devices actually works. Picture this. You're streaming a 4K video on your couch, totally flawless, right? But the second you take 2 steps behind the kitchen wall to grab a snack, buffering. Ugh, it's a completely universal frustration. But to figure out exactly why your signal just vanished into thin air, we actually have to dive into the physics of wireless connectivity.
Okay, let's dive into this. Here is our roadmap to make all this complex networking jargon totally manageable. 1. The wireless world. 2. Frequencies, range versus speed. 3. Hardware, access points. 4. The evolution of Wi-Fi. And 5. The future, Wi-Fi 7. Let's start with Section 1, the wireless world, and decoding IEEE 802.11. At its absolute core, Wi-Fi is really just invisible radio waves. The IEEE 802.11 standards are just the rules governing how we push data across 3 main frequency bands, 2.4, 5, and the newly added 6 gigahertz. These invisible waves are the literal carriers of our entire digital lives. Moving right along to Section 2, frequencies, range versus speed, or basically the physics of Wi-Fi. And this brilliantly illustrates the daily trade-off we all make without even realizing it. It's the classic battle of distance versus speed. Think of the 2.4 gigahertz band as your marathon runner. It's got fantastic range and great wall penetration, but, lower data speeds. Now the 5 and 6 gigahertz bands, those are your sprinters. You get absolutely blistering speeds, but a much, much shorter range, and honestly, pretty terrible wall penetration. So, that dreaded kitchen drop-off we talked about earlier, yeah, you were likely connected to a super fast 5 gigahertz band that just couldn't punch its way through the drywall. Section 3, hardware, access points, and grounding the invisible. So to ground all these invisible waves, we need a wireless access point, or an AP. This is the physical device that bridges all your wireless gadgets to a physical wired network, creating what's called a wireless local area network, or WLAN. But actually designing this coverage isn't just plug and play. It requires a really careful balancing act of frequency types, physical barriers like those annoying walls, and of course, user density. Now, to clarify how we actually interact with these devices on a daily basis, we have something called infrastructure mode. Simply put, this is the standard operational mode where clients, like your smartphones, your laptops, your smart TVs, connect directly to an access point. It's literally the backbone of almost all of our day-to-day home and office networks. Section 4, the evolution of Wi-Fi. Let's take a chronological journey. Now that we've got the physics and hardware down, let's see how this tech has evolved to solve our problems. The journey officially kicks off back in 1999 with 802.11a and B, followed by G in 2003. But let's be real, consumers needed something way simpler than a bunch of random letters. So the industry wised up and introduced Wi-Fi 4 alongside the 802.11n standard in 2009. A total game changer for clarity, right? This paved the way for Wi-Fi 5, and then Wi-Fi 6 and 6E, which rolled out between 2019 and 2021. And the technological leaps matching these new consumer names, they were massive. Wi-Fi 4 introduced MIMO, which stands for Multiple Input, Multiple Output. This basically meant using multiple antennas to send and receive data at the exact same time, hitting speeds up to 600 megabits per second. Then Wi-Fi 5 stepped it up big time on the 5 gigahertz band. It brought wider channels and multi-user MIMO, allowing routers to talk to a bunch of devices simultaneously, pushing speeds well over 1 gigabyte. So the crucial point is that as we move to 802.11ax, or Wi-Fi 6, the game entirely changed from just raw speed to sheer capacity. Think about being in high-density areas like crowded airports or packed sports stadiums. Wi-Fi 6 is heavily preferred there due to its superior efficiency. By cleverly leveraging the 2.4, 5, and the new 6 gigahertz bands, it provides massive capacity right where hundreds or even thousands of devices are actively fighting for the exact same invisible airspace. When you look at the overall progression here, the pace of innovation is honestly staggering. Way back in 1999, 802.11b maxed out at just 11 megabits per second. Fast forward a bit, Wi-Fi 4 hits 600 megabits, Wi-Fi 5 completely shatters the gigabit barrier, and then Wi-Fi 6 takes theoretical max rates all the way up to 9.6 gigabits per second across 3 separate frequency bands.
Let's move to Section 5 and see how this builds into the future. The future, Wi-Fi 7, breaking the speed limit.
46 gigabits per second. Just let that number sink in. That is the maximum theoretical data rate for the brand new 802.11b standard, officially known to the rest of us as Wi-Fi 7. Operating simultaneously across the 2.4, 5, and 6 gigahertz bands, Wi-Fi 7 is designed to offer speeds and network efficiency that literally dwarf absolutely everything that has come before it. Which really leaves us with a fascinating question to chew on. In just a couple of decades, we've gone from a sluggish 11 megabits per second to a truly staggering 46 gigabits per second. We've tackled the wall penetration issue, we've solved stadium density, and now we are unlocking raw, unadulterated bandwidth. With this ultimate wireless freedom now at our fingertips, what incredible technologies are we going to build next? It's kind of mind-blowing to think about. Keep asking those great questions, and thanks for joining me on this explainer.
Thanks for watching.